Hi everybody. So we are currently going to begin chapter 3 in statics. If you take a look at our Moodle page, first of all, you can see that we are done with chapters 1 and 2. You should have by now turned in homework number 1, which was the handout on unit conversions, and homework number 2, which is chapter 2. There's no actual homework problems in the textbook of chapter 1. You should also have completed the quiz over chapters 1 and 2. And so today we begin lecture 10 with coverage of section 3.1. So at the end of this lecture today, this assignment button, the blue with the arrow in the middle, will be replaced with a link, and that will be what you're watching as you're watching this video. So having said that, chapter 3 starts to talk about rigid bodies and equivalent forces of systems. The topic here is really about the fact it's still absolutely true that in order for a body to be in static equilibrium, in other words, to be sitting still, that you have to have the summation of forces in the x, the summation of forces y, and the summation of forces z directions have to be equal 0. That is absolutely true. It is just not enough. If you can't consider the body to be a point, in other words, if it has a shape and a size, putting two equivalent forces on it may actually cause it to rotate. For example, if you had a rectangle, a shape like this, right, and you put a downward force here and an upward force here, and the magnitude of direction was the same, and the sense or the direction was opposite, you would have summation forces y equals 0. But if you actually applied those two, it would tend to cause the body to spin. So there's more to it than just the forces. And what that more to it is moments. So in this chapter, we're going to start talking about moments. Now, moments are a cross product of two vectors. So in section 3.1, we're going to do a review of some vector math, and we're going to talk about vector multiplication and a little bit about addition. Now, this is not a complete discussion, but what we're doing is we are taking the pieces of vector math that we need in order to execute vectors properly and to do the vector math associated with forces and moments and equilibrium of rigid bodies. So the difference between a particle and a body is just in real life everything is a body, but sometimes there's enough symmetry or it's small enough that you can consider it just to be a single point. So for a body of any size or shape other than completely symmetrical, we need to consider those elements as well. Now, a rigid body means that the body will not deform or break under the loads that we subject it to. Later on, when you take mechanics of materials, you'll learn how to deal with non-rigid bodies where things deform or break. But in this class, we assume that everything we apply to the body will be taken up by the body without deformation or without breakage. So we are going to look at a few different things. We're going to talk about the moment of a force about a point, the moment of a force about an axis, and the moment due to a couple, which is a couple is just like what I described earlier. If we have a downward and an upward force on a rectangle and the sum of forces equals 0, but the equal magnitude opposite direction forces will tend to produce a rotation. That type of a force system is called a couple. And the last point on this slide, any system of forces acting on a rigid body can be replaced by an equivalent system consisting of one force and one couple. So this is similar. It's an extrapolation of the idea that we had where we had like a tugboat and two ropes pulling the tugboat. What would an equivalent force be? In other words, what one rope magnitude and direction could we substitute for the two? And instead of having that force system, just have one. So now we're saying that even if we're talking about this possibility not just to translate but to rotate, we can replace that with a very simple force couple system. and that's actually referred to as a wrench. So there are two different kinds of forces, external and internal. When you draw a rigid body diagram, when you draw a free body diagram, the external forces are shown as what's going on. For example, if we're talking about this truck, there are people pulling on the truck, there are wheels, there's weight. So we refer to the road pushing back up on the tires, the weight pushing down, and the people pulling it forward. And in order for static equilibrium to be maintained, all of those forces have to be opposed. And as I said, also, we have to take into account this idea of rotation as well, even if the forces are equal and opposite. But if you look at this truck, for example, if you pulled on this and there was nothing opposing it, in this case the opposition would be friction, the truck is going to move forward. And so in order for it to maintain static equilibrium, you cannot pull forward with more force than friction will oppose that force. The next very important idea is this principle of transmissibility, which says if you take a line segment, really, and you draw it through the line of action of a force, that you can move the force anywhere along that line of action and it will produce the same result. This is referred to as transmitting a force along a line of action. So on this blob, which is kind of like it kind of looks like a blobby potato, on this potato, the force F and the force F prime would have the same effect, and that is why they are considered to be equivalent forces. Now, if you look at something like this truck, moving the point of application of the force to the rear bumper does not affect the motion of the truck. In other words, pulling on the truck or pushing on the truck, as long as it's along the same line of action, has the same effect on the truck. So the principle of transmissibility may not always apply in determining internal forces and deformations, but for our purposes we can discuss that, and we can consider it generally true at this stage of the conversation. So now we do a little bit of vector math. If we have two vectors, in this case we have P and Q, which are separated by some angle theta, they both go through this point, which I would refer to as 0, and the product of these vectors, in other words, if I multiply P by Q, we will have a vector called V. And V, which is itself a vector, is perpendicular to both P and Q. In other words, whatever plane P and Q form, V will be perpendicular to it. It will either be up or down, in this case, if you consider P and Q to be in a horizontal plane. Now, whether V is positive or negative is determined by the right-hand rule. So you take your hand, right, and you form it into, you take your right hand, it's going to be backward because of this, but you form it into a V. You take P, fold it into Q, and the direction of V, if it's up in this case, would be positive. If it were down, in other words, P or Q folded into P, would be negative, which gives us sort of our first fact about vector products, is that vector products, which are also called cross products, are not commutative. That Q crossed with P is in fact equal to negative P crossed with Q. Also not distributive and not associative. So they're very specific in terms of how the vector math works. So this is just a description of the right-hand rule and forming vectors and vector products in terms of rectangular coordinates. So in the most general sense, we could call that vector P, P sub xi plus P sub yj plus P sub zk, and similarly for Q. Then we would find that the ij and k components of that vector break up into, I guess you would say, alternating, what am I trying to say? Like if it's an I directional, if it's the I part, the x part, only the y's and z's will apply. That's because of that perpendicular nature, and this actually works out a sign in the process. But you can evaluate this more easily by doing what's called a determinant, evaluating a determinant, which is a value that you get from a square matrix, so 3 by 3 matrix in this case. So you can write this entire thing as ijk being the first row of your array, which is a general word for matrix, or determinant is actually the evaluated value. So, but it's a matrix is a type of an array. Then the first line is, if it's P cross Q, this would be P sub X, P sub Y, P sub Z. And then the final line would be Q sub X, Q sub Y, Q sub Z. Now, if you were multiplying Q by P and getting a vector product, in other words, Q cross P, Q would be on this line, P's would be on this line. And this just shows you the direction. I times J is K, and so forth. So in other words, what this is saying is that counterclockwise is positive. J times K is a positive I. If you go backward clockwise, it's negative. And that corresponds with the right-hand rule. But if you do this using a determinant, it will always work out in terms of the sign, because if P and Q are not in a particular plane, like a horizontal plane or a vertical plane, V is going to be perpendicular to it no matter what. So in other words, if the plane of P and Q are at some angle, V is going to be perpendicular to that plane. It's not going to be purely IJ or K. All right, so the moment of force about a point, this is something that we are going to do for quite some time. This is actually something that we're going to use to establish the rotational as well as the translational equilibrium of a body. So the moment of a force has to be defined about a point, and it's R cross F. R is the vector that extends from point O to any point on the line of action of F. So you can think of it as being the beginning of the force, but if there's an easier point on the force, or even on the line of action of the force, you can take it to that as well. And evaluating that determinant will work it out. But it's going to be R, the distance from O to that point, crossed with F, which is F sub X, I, F sub Y, J, F sub Z, K. The moment is perpendicular to the plane containing O and the force. That's always, once again, getting back to that perpendicular nature. And the magnitude measures the tendency of the force to rotate. So you always see, they always draw pictures of a person's hand with the moment, the vector of the moment, or the vector of the moment, M sub O, showing its direction. And he's curling his hand here. She is curling her hand this way, and the thumb is pointing up, indicating a positive moment. This has limited use mathematically, because quite frankly, this only applies when the two vectors R and F are in a single plane, up and down. Negative or positive, and understanding that moment may be may have negative I, positive J, negative K, or something similar to that, is more important, and it comes about through doing the vector math rather than this, which is relatively a shortcut. Sometimes useful, but it's more useful to learn how to evaluate a determinant. So here's just some forces, or some points about forces and the moments that they create about different points. If you have a two-dimensional structure, so in other words, this is not a potato, this is a cardboard cutout of a potato, they have length and breadth but negligible depth, and they're subjected to forces in that plane, because a plane perpendicular or askew to this does not exist in two-dimensional land. Everything happens in the plane of the board. The plane of the structure contains O and F, and the moment is going to be perpendicular. So they draw it, because we really can't draw something coming out of the page. It would just look like a dot. They draw it as a rotation. And if the object, if you put a pin in O, pulled on F, and rotated it, that rotation is going to indicate the positive or negative nature of the moment. And so quite honestly, if you look at this, if it's R cross F or D cross F, M is going to go into the board, and that means it's negative in the sense of an XY plane in the plane of the board, with Z coming out as positive and Z going in as negative. So this little negative sign just indicates the negative nature of that moment. Also, another thing you might notice, this rotation is counterclockwise, or clockwise rather. A clockwise rotation corresponds to a negative moment using the right-hand rule, and a counterclockwise moment corresponds to a positive moment using the right-hand rule. So for example, put your hand along D, fold F into it. There we go, that's better. Put your hand along D, fold F into it, and your thumb comes out of the board. The rotation is counterclockwise. Both of those things mean positive. All right, Varignon's theorem talks about what if you have one moment and several forces? Well, you can add the forces together vectorially, and then you can cross them. You can cross R with that sum, that vector sum, or you can individually break out each of those forces and cross them with R. So, in other words, this almost looks like the distributive property, doesn't it? So Varignon's theorem makes it possible to replace the direct determination of a moment by the moment of two or more components. And sometimes that is very handy as a solution technique. All right, so if we start talking about 3 dimensions, we have to rely upon the array and the evaluation of that determinant. This shows you how to find m sub o. Now this has a vector, a little arrow over it, meaning that we're talking about the vector, the moment about o. So here's point O, and we're talking about the moment built in by the force F. Okay, so we have, these are the 3 components, I, J, and K of F. So the first row is I, J, K, the unit vectors. The second row is X, Y, Z. That means the X distance along R, along the moment arm is what R is called, from 0 to R, and the same in the Y and the Z direction, and then the components of force. Then this just shows you what that breaks down to. So like I was saying, in the I direction we have all Y's and Z's. In the J direction we have all Z's and X's, and in the K direction we have all X's and Y's. So everything is mutually perpendicular. So this is just talking about the fact that if you have point B, that if you know something about point O, you can kind of subtract point A from point B in order to get that vector. So you're looking at the difference between those vectors, between those points, to establish the vector. Now in 2-dimensional structures, it's much easier because the moment is always going to be purely Z, and it's always going to be this product and difference of that product in the Z direction if the plane that you're using is the YZ plane. And we'll do some practice with this later this week. We're going to cover sections 3.1 and 3.2 before we have a practice day. So the 3.1 talks about a sample problem. We have a 100-pound vertical force, that would be this, and it's applied to this lever. So in other words, if we're finding the moment about point O, there might be a pin or something there, and we want to know the magnitude of that moment. We have a force and we have a vector R, and we know an angle. So we can find all of these pieces of the puzzle. We can find the moment about O, the horizontal force, which creates the same moment, the smallest force at A, which creates the same moment, the location for a 240-pound vertical force to produce the same moment. So just a hint, if this is 100 pounds and this distance is 24, if we're going to compute the same moment about point O and we have a longer force or larger force, we're going to have a shorter distance, aren't we? So the first thing we do is compute the moment about O. It's just the force times the perpendicular distance. In other words, if this is vertical, all we're interested in is the horizontal distance. So here we're not using a determinant, but we're just taking 24 times the cosine of 60 to find out what this horizontal distance is. Then we multiply it by the magnitude of the force, and we decide if it's positive or negative. In this case, if you think about putting a pin here at 0 and pulling on it with that force, you'll see that it would spin in a clockwise direction. Clockwise in terms of the right-hand rule means that it's negative. This states it's positive. It's a change in it's a change from the right-hand rule. It's acceptable in 2 dimensions, but I would refer to this as a negative 1,200 inch-pound force at moment. So forces are measured in pounds, distances are measured in inches or feet. And so moments are measured in inch-pounds or foot-pounds in the SI system, measured in Newton meters. So now we want to find out what horizontal force that A would apply. It's going to be a smaller force, because now we're talking about this vertical distance d. Horizontal force times vertical distance equals moment. We want to find a 1200 inch-pound moment, so we can find the force using that math. And then the smallest force A that will produce that same moment. Well, if you think about the equation, how do we make it the smallest force? By making it the largest d. That means that we want to have the cosine, the angle between them 90 degrees. In other words, if you have a moment arm, the smallest force to produce that same moment is going to be perpendicular to the moment arm. So we draw force perpendicular to the moment arm, and if you look back at the last problem, when we talked about we take the sine of 60, so in our case we would be mathematically talking about the sine of 90 degrees, which is 1, and that's as big as a sine gets, right? Sines go back and forth between -1 and +1, so the biggest value you can reach is +1. All right, and then we can talk about, like I said, you're going to have to shorten up that moment arm in order to produce the same moment with a shorter moment arm. That's kind of similar to the idea of kids on a teeter-totter. In other words, if you have an even length teeter-totter, you can put equal weight children on both sides and they'll be well balanced. But if you have your kid brother on one side and you're on this side, you get a shorter moment arm, or else you're going to get to put him up every single time. And as teeter-totters are a really good example of a moment arm and a weight acting initially perpendicular to the moment arm, and then later the weight doesn't change direction, but the moment arm does as the seesaw or teeter-totter tips up and down. All right, and sample problem 3.4, we'll just construct this a little bit, and we'll talk about this when we do problems later this week. But we want to find the moment of the force exerted by a wire. Okay, and so this wire is plugged in here at point D. So the wire runs from D to C, but the force is pulling up, isn't it? It's pulling upward on the plate. And we know that the tension, that value is 200 newtons. We want to find the moment about point A. So that means that the moment arm is going to be from A to any point on the line of action of CD. So we could find it to C, but it looks to me like it would be quite easy to find it up to D. So my R would be from A to D. My force would be from C to D. I know the tension, and I can work out the geometry just like I did with standard forces. So basically, we say that the moment about point A is equal to R from C to A, which they're comfortable finding. We could have also found from D to A. Then the force, the tension is pulling up, so we find lambda along that force, multiply it by the magnitude which we're given, and we compute a value of the moment, which is has a negative I component, a positive J component, and a positive K component. All right, so ladies and gentlemen, that's it for today. That covers section 3.1, and this will be lecture 10 in statics. I'll do section 11, or lecture 11, which will cover section 3.2, and then we'll spend a day doing problems. So thank you for attention, and we'll see you in class.